Good morning, student. Myself, Mrs. Shalini Singh, Senior Assistant Professor, School of Pharmacy, BBD University. Today, I am going to discuss the topic isomerism. Contents are introduction, types of isomerism, structural isomerism, stereoisomerism, geometrical isomerism, optical isomerism. What is isomerism? Compounds having same molecular formula but having different physical and chemical properties are known as isomers, and this phenomena is known as isomerism. This difference in properties are due to different arrangement of atoms within the molecule. Examples are N-butane and isobutane. Now comes to the types of isomerism. There are two types of isomerism. First one is structural isomerism and second one is stereoisomerism. Now come to the structural isomerism. Two or more compounds with the same molecular formula but different structural formula are known as structural isomers, and this phenomena is called structural isomerism. Stereoisomerism. What is stereoisomerism? The phenomena of isomerism exhibited by two or more compounds with identical molecular and structural formula but different spatial arrangement of atoms or groups is known as stereoisomerism. Structural isomerism is further divided into three parts: chain isomerism, position isomerism, and functional group isomerism. Stereoisomerism is further divided into two parts. First one is geometrical isomerism and second one is optical isomerism. What is geometrical isomerism? This isomerism is caused by the difference in spatial arrangement of groups about the double bonded carbon atom is known as geometrical isomerism. The two isomers can be distinguished from each other by the term cis and trans. The second one is optical isomerism. It is a type of stereoisomerism in which molecules have same molecular and structural formula but they are differ in the behavior towards light, or we can say they are differ in their effect on the rotation of plane polarized light. Under the category of structural isomer, first one is chain isomerism. These isomers show similar chemical properties because the same functional group is present. Physical properties such as density and boiling point show trends according to the degree of branching. Boiling points gets changed sometimes. Straight chain isomers have higher values than branched ones. The greater the degree of branching, the lower the boiling point, because branching decreases the effectiveness of intermolecular forces so that less energy has to be put in to separate the molecule. Here we can see that two molecules are present. First one is a straight chain molecule and second one is branched molecule. The boiling point of the straight chain molecule is minus 0.5 degrees Celsius, whereas in the branched molecule boiling point is minus 11.7 degrees Celsius, because less energy has to be put in to separate the branched molecule. Second one is positional isomerism. Here the isomers have the same carbon skeleton. Molecules has the same functional group but the functional group is in a different position. They have similar chemical properties but different physical properties. Examples is pent-1-ene and pent-2-ene. Here we can see the difference is in the position of the double bond present. In pent-1-ene the position of double bond is on the first carbon, and in pent-2-ene position of double bond is to second carbon. Another example is 1,2-dichlorobenzene, 1,3-dichlorobenzene and 1,4-dichlorobenzene. Here we can clearly see that the difference is only on the position of chlorine present on the benzene ring. Third one is functional group isomerism. These isomers have same molecular formula. They have different functional groups. Molecules have different chemical properties and different physical properties as well. Examples are alcohol and ethers, aldehyde and ketones, acids and esters. Now come to the topic stereoisomerism. This is the second type of stereoisomerism. The phenomena of isomerism exhibited by two or more compounds with identical molecular and structural formula but different spatial arrangement of atoms or group is known as stereoisomerism. There are two types of stereoisomerism found. First one is geometrical isomerism. This isomerism is caused by the difference in spatial arrangement of groups about the double bonded carbon atom is known as geometrical isomerism. Now come to the optical isomers. It is a type of stereoisomerism in which the molecules have same molecular and structural formula but They are differ in the behavior towards light, or we can say they differ in their effect on the rotation of plane polarized light. Geometrical isomerism in alkenes. It is an example of stereoisomers. It is found in some but not all alkenes. It occurs due to the restricted rotation of carbon-carbon double bond, and it get two forms, or we can say the two isomers can be distinguished from each other by the term cis and trans. In the cis or Z system of nomenclature, groups or atoms are on the same side of the double bond, whereas on the trans or E type of nomenclature, groups or atoms are on opposite sides across the double bond. Single covalent bonds can easily rotate. What appears to be a different structure is not. It looks like it, but due to the way structure are written out, they are the same. All these structure you can see are the same because the carbon-carbon single bonds have free rotation. As we can see that the free rotation is present in between the carbon-carbon single bond. Carbon-carbon double bonds have restricted rotation, so the group on the either end of the bond are frozen in one position. It is not easy to flip between the two. This produces two possibilities. The two structures cannot interchange easily, so the atoms in the two molecules occupy different positions in the space. It is another type of isomers, that is cis and trans. It is also known as E and Z type of nomenclature for the isomerism. In the Z, higher priority groups or atoms are on the same side of carbon-carbon double bond, and on the E, higher priority groups or atoms on the opposite sides of the carbon-carbon double bond. To determine the priority, the Can-Ingold and Tree-Log convention is used. Whereas some rules are given under the Can-Ingold and Tree-Log convention, and according to that priority get decided. Cis or trans should only be used when there are two hydrogens and two non-hydrogen groups attached to each other. In the cis, non-hydrogen groups or atoms on the same side of the carbon-carbon double bond, and in trans, non-hydrogen groups or atoms are present on the opposite sides of the carbon-carbon double bond. Optical isomerism. What is optical isomerism? It is a type of stereoisomerism in which molecules have same molecular and structural formula, but they are differ in the behavior towards light, or we can say they differ in the effect on their rotation of plane polarized light. It is another form of stereoisomerism. It occurs when compounds have non-superimposable mirror image. The two different forms are known as optical isomers or enantiomers, and they occur when molecules have a chiral center. A chiral center contains an asymmetric carbon atom, and asymmetric carbon has 4 different atoms or groups arranged tetrahedrally around it. Optical isomerism. Two forms exist which are non-superimposable mirror image of each other. Non-superimposable means you cannot stack one form exactly on the top of the other, as you can see in the picture. Mirror image and non-superimposable, superimposable but not mirror image, that is books. Another example is non-superimposable mirror image are hands. Isomers, optical isomers differ in their reaction to plane polarized light, as I have earlier said that they differ in their effect on the rotation of plane polarized light. Plane polarized light vibrates in one direction only. One isomer rotates lights to the right, the other to the left. Rotation of light is measured using a polarimeter. Rotation is measured by observing the polarized light coming out towards the observer. Optical isomerism. This is a picture of polarimeter where A is the light source, produces light vibrating in all direction. As you can see, B is the polarizing filter. It only allows through light vibrating in one direction. C is the plane polarized light passes through the sample. Here the sample is kept in the C part. D, if the substance is optically active, then it rotates the plane polarized light in either direction. E is the analyzing filter is turned so that the light reaches to a maximum, and F is the direction of rotation is measured coming towards the observer. So direction of rotation is measured and it is decided that the compound is dextrorotatory or levorotatory. If it turned light to the right direction, it is called dextrorotatory, and if it turned to the light to the left direction, it is called levorotatory. Thank you.